Welcome to the Valve Studio. Our work on this JCM800 continues. Last time we were fussing around with the tubes and we were looking at the tube tester, and I found some problems that needed to be calibrated. I'm not going to go into that. In fact, I take that whole thing out of the picture here. Let's just go back to the amplifier and kind of look at it, just assuming that the tubes that I got from Jerry are gonna function. So that's what we're going to do today. We're going to actually pull up the plate characteristic for that. We're going to run it through our little analysis tool. It's very similar to the way that I did the Pintode for the Mectron record player. And we're going to actually use Python's IPython notebook to plot the load line. And we need to have that in order for us to really understand where we should set the bias point. There's a lot of discussion about setting the bias point out on the net. Some people say set it to 70% of the power dissipation. This particular tube is a 25 watt tube, so pick 70% and then dial it into that. Other people say 60%. Some people say don't even do that, just tune it up to ear and then make sure you're under the power dissipation. All those are valid, but how would we really want to look at it from more of a technical, an engineering approach? So we're going to plot the load line, and we're going to try to figure out where should we pick the bias point such that our entire operation is under the 25 watt limit, and we're going to do that. Then we're going to come back over to the bench here, and we're going to take some measurements to confirm our initial analysis of the DC operating point, and I'm going to show you that I found some additional prompts as well, and I finally get to use both of my milliamp meters. These, remember, came from the Jim Taylor estate sale in Los Alamos, and I get to use both of them, and so we can look at both anode currents at the same time. And I don't need to disconnect anything because these are clip-on milliamp meters. There's a lot of work out there, a lot of videos on how to, insert a 1 ohm resistor into the anode lead or the cathode lead on these EL34s on these big power amplifiers. There's a problem with that though. When you do it that way, you also add in the screen current. And on these particular tubes, that screen current down at the bias point that we're at is almost 10%. So if you set it at 30, the screen current might be 3 milliamps. So you're really setting it at 27, not at 30. So you need to take that into account. But fortunately for us, we don't need to fuss with that today. We're going to use these clip-on milliamp meters, and we're going to actually clip on the wire that goes from the anode right over to the output transformer. It's going to give us a really accurate result, and we're going to ultimately find some additional problems. Let's go ahead and get started with the analysis, then we'll come back over to the bench, and we'll get that all done for today, and we'll see where we get, because at the end of it, we got to get this thing working. All right.
Take one. Okay, the schematic for the 2205, this is a JCM800, comes in two parts. This is the preamplifier side, and this is the power amplifier as well as the power supply. First thing I want you to notice is down here, this date on this drawing is 12/3/87, and the latest revision is 4/5/88. So this is about 6 months after mine was actually manufactured. My amplifier does have these 5K resistors in here. Okay, the first thing I want to look at is here's the power transformer. We need to figure out what the power transformer actually is. So I looked up JCM800 replacement power transformer, and I came across this one from Classic Tone. If I can get over there, here we go. So the thing you want to notice is this is 690 volts center tapped. So that means that on one side of this is going to be 690 divided by 2, and that number is 345, which means that the peak voltage on that is going to be that number, 345 RMS. The peak voltage is the square root of 2 times that, which ends up being 488 volts. All right, so let me get back over my schematic. So we have peak voltage right here of 488 volts. We have this full-wave rectifier made with these diodes themselves. These diodes aren't going to have much of a voltage drop. They may combined have a voltage drop of 1 volt. So we're really around 487 volts right about here. Going to not get a voltage drop on the fuse, and then there's a little bit of current going through the choke to feed all the preamp, as well as the screen current on the output tubes. This side over here, this is the main output transformer. So the plate current times 2 is going through this side over here. I estimated all this kind of stuff at, let me bring up my estimation here. There's actually 5 EC83s, so each one of the triodes in it draws about 1 milliamp, so that's 10 milliamps. And then these guys here I kind of guessed at about 4 milliamps a piece. So we got 2 times 4.4, actually I kind of came up with 4.4. And 5, there's plus all the EC83s. I think it's going to be maybe about 100, maybe about 18 milliamps, 19 milliamps. This choke is 110 ohms DC. So I kind of estimate this voltage over here to be 485. Now we're working all this stuff because we want two kind of numbers out of this phase of the analysis. We need to know what the screen voltage is right here. And I'll tell you about why that's important in just a minute. We need to know that, and we also need to know what the bias voltage is set at right here. So this is a fixed bias topology. There's another half-wave rectifier that's brought off of one phase of the power transformer, and it goes through this half-wave rectifier here. It's filtered through this capacitor. But there's a string of resistors over here. This is a voltage divider so that we can kind of have a little bit of flexibility in where we set the bias point. I went through and I measured, I calculated out all this, using the RMS value, and then half-wave rectifier is 0.45 times RMS, and blah, blah, blah. And I came up with minus 59 volts right here. And it turns out that this volt, I don't have it written on this piece of paper, but this one right here is about calculated, I think, to be minus 38. All right, so then I went and I turned the amplifier on, and I got some numbers that are a little bit different than this, but we'll go through those. The blue numbers are my measured values. So I started measuring and I was kind of vastly off by maybe 30 volts. So I'm off by 10%. Well, I went and I opened up this fuse and I verified that the transformer is actually functioning correctly and the rectifiers. So with the fuse open, we got 490 volts and I estimated 487. So I'm correct here. What I didn't really calculate very well is the voltage drop that occurs inside the power transformer. And what that ended up doing was it kicked down all the voltages by about 30 volts. So when it was actually all on and kind of warmed up, what was happening over here was I didn't get 487 volts out, I got 455. So if you go through and you look at all these numbers, the blue numbers are the measured values. The two numbers that are important out of this is what is the screen voltage here? It's 445. And then down here, we are at minus 37. So we're looking pretty good there. All right, now why is this important? Let's go over to the data sheet. We're going to go look at the Philips data sheet for this device. This is the EL34. It's the Philips data sheet from like 1955 or something like that. And what you're going to find down here after a bunch of tables is the plate characteristics. They typically give you plate characteristics and a couple of voltages. You can kind of see here, I don't need to rotate this. I'm going to leave it this orientation. I'll show you why in a minute. We got this one here at 250 volts, and then down below it we have another one at 360 volts. So what I ended up doing is I actually created some PNG files from this, so we'll take a look at those. Those are over here. Okay, so here are the two curves. We got the 250 volt. This is for the grid voltage the screen voltage at 250 volts. And then this is the one for 360. Now, what's important to know is that a lot of times in amplifier design, your screen voltage doesn't match up with the data sheet. You can design it that way, but sometimes it doesn't. In this case, in our case here, it does not, because our screen voltage was what, 445 right here, 445. So do we still get some information out of these graphs? Yes, we do. I want you to look particularly at these two graphs and a couple things that happen. 250 volts at when the control grid is at 0, we cross this power at 25 watts. We cross this line at about 250 milliamps. Now down here at 360, when control voltage is 0, we cross it at about 375. The other thing to notice is this range on the control grid goes from 0 to minus 25. On this graph, we go from 0 to minus 32, so we have 7 more volts of swing on the grid. The other thing is that we're at minus 32, we're way out here at 650, and we're kind of off the graph over here, so we don't really know what that's going to be. All right, how do we interpolate these two graphs to give us something at 450 volts? What's happening is as you increase the screen voltage, this graph grows up. So all these lines make a move upwards. And what's going to happen is as we go to minus 450 volts, we're going to get another 7 or 8 volts of potential down here to get all the way down to cutoff. So we're going to have more lines on this, but they're going to go up higher. So it might go up to here, you know. It's going to be off this graph. So how does that help us now? Can we guess what that is? No. Let's not do that. Let's go and look at if we were at 360 volts. And let's actually look at the impact of the load line at 360 volts and then just kind of ballpark guess where we're going to be when we're actually at 450. I created a Jupyter Notebook for the Marshall amplifier biasing, just like I did for the Mectron record player. The JCM800 is a push-pull amplifier using EL34s. So you can kind of see it here. I'll go ahead and go full screen here. I did the same kind of thing. I took the Philips datasheet for the EL34 at 360 volts, ran it through Engage, and actually got the data out of this. Here's that same schematic that we were looking at before. I wrote a couple references in here from the Valve Wizard. We'll go ahead and bring up that as well. This is where I got the majority of the information, and I confirmed it with a couple of other sites. And it's a pretty good explanation of what's actually going on. Gets a little kind of funky down here, but you can go ahead and take a look at that if you want to look at what I was reading about. The other one is from Aiken Amplification about why the 70%. This one also is very interesting, and gets down to the end. Randall gets down to the end, and he shows you a bunch of graphs down here. So I'll go ahead and show you how he generated these graphs. This is the really most important part of determining the bias point and where the 70% came from. So we'll get down to that in just a few minutes. And this is all included in my Jupyter Notebook. All right. He also has a little program that he used to calculate this. He wrote it in C++. We're doing the same type of thing in Python here. All right, so let's go down to here. I brought in all this data. You can kind of see this is all the curves. It's the beginning, the head, and the tail of the data file. And then there's a bunch of setup values right here. IA, which is the bias current, and the anode voltage, the load, and the turns ratio on the transformer. And how do we come up with all these things? Where do we get this from? I got all this from the Mullard datasheet. This is for the EL34. I went through here and I looked at these various operating conditions tables. So let's go take a look at some of these and I'll tell you how I figured out which one to use. This one's for a single valve class A. That's not us because we're push-pull and we actually are AB1. Here's 2 valves push-pull, 430. And, distributed load using screen tapping at 43%. This is for ultralinear operation. That's not us. Operating conditions with fixed bias. That's us. Okay, fixed bias because we're not using cathode biasing. If you come back up here and look at our circuit, we are biased using fixed bias, which is this circuit down here. Remember, we're at minus 37 volts. All right, so this is a contender. Let's keep going down here. Here's 2 more that has a screen good supply and fixed bias at 500 volts. This one's also fairly close as well. A little higher voltage. This one's a really high voltage. It's 800 and 400. This is definitely not us. Okay. Plus, you can actually look at something else down here. The power output on this is 70 watts. Here's 100 watts. Here's 35 watts. Remember this JCM800 is a 50 watt amplifier. Down here, triode running the pentode is in triode connection to Class A. For a single valve, this is not us. This is more triode connection. All right, so that's pretty much it, and we get into the physical dimensions. So we're going to go back up, and I actually found most of I used this column in this table right here. Let's take a look at this. VB, which is the battery voltage, I'm calling that VA in my, I probably should change this in my Jupyter Notebooks. VB is 425. Remember, we're at 450. If you come back here again, we're at 453. RG2 is 1,000. This is actually what caught my eye, is that 1,000 right there, because wouldn't you know it, our screen resistor is a 1K resistor right here. IA is 30, and they say that IG2, which is the screen current, is 4.4. So this is where I got the 4.4 from. If you come back here and you look at this, my estimate up here was that the screen current is 2 times 2, 4.4. That's where I got the 4.4 from. Our fixed grid bias is at minus 38 volts. That's the calculated value right here. Our measured value was minus 37. RAA is 3.4. The 3.4K. All right, this is an important thing right here because this actually sets the slope of the line for the load line. And if you come in and you divide 3,400 by 8 ohms, and you take the square root of that, you get 20.6. All right, 20.6. Effectively, that's 21 turns. And that is where I have the that table in there. Where's that thing? N equals 21. Okay, so I'm using an 8 ohm speaker, and my turns ratio is 21. Power dissipation is 25 watts. Okay, so also P out's 55 volts. Now, here's a little bit of a disconnect from what we're trying to do here. Their plate voltage is 425. Ours is, where's my graph here? Ours was 453. Okay, but we don't have a table at 453. We're actually using this set of data when our VG2 is at 360. But our measured value for VG2 is 445. So we're going to be a little bit off.
But you'll kind of get the gist of what we're trying to do here. Just remember that when you kick this back up here from 460 up to where we'd measure things at 445, all these curves get kind of expanded up. So what ends up happening is this thing goes down here. These last two curves down the bottom, one might be minus 36 and the last one might be minus 40. So all these curves are kind of pushed up. But let's see what happens when we're at 460, just because this is how we have the data. All right, so we come back down to come all the way down here, and here's our load line. This is where it gets kind of funky. And I actually learned a lot about how this works by figuring all this out. This particular amplifier is a Class AB1 amplifier. And because of that, it runs in Class A for very small signals and then switches over to Class AB1 for larger signals. And if you look at this graph here, we have these two sloping load lines. This first one is for when the output signal is very small, and it actually is running in Class A. In Class A, where both valves are actually conducting because their output signal is small enough, and they're just kind of doing both push-pull at the same time. At some point they cross over and one of them turns off and the other one goes into Class AB mode, and it switches the impedance because the transformer is in the picture between the output tubes and the speaker. When you're running in Class A and you're doing push-pull, the reflected impedance is half of that RAA value. So this slope of this line is actually going to be that 3400 divided by 2, which is 1764. When it switches over in the Class AB1, it is now divided by 4. So that's what 882. So this thing has this kind of this knee in it. Now this graph is drawn as a knee, but it's actually not so abrupt like this. When these curves here, there's a statement in the one of these other sheets, I think on the Valve Wizard. He says that it's not really abrupt like this, like I've got written here. It actually is very smooth and gradual. And that is because these curves down here are kind of smashed together when you get down in here. And you got two tubes kind of working at the same time. And so this is really gradual, and it kind of just makes this change without a discontinuity right there at this single point. But for what we're doing, this here is actually going to demonstrate something that's really pretty important. The important thing to look at is this operation right here is clearly in excess of this 25 watts. So now what, are we going to blow the tubes out if we do this? But keep in mind though, when you're doing this upper tube is on for only half of the cycle when it's running up in here. So because of that, the average power across a complete sine wave effectively is not this value here. So what is it? This is what was kind of took me a little while to come up with this notebook, because what I ended up doing was I integrate the a waveform while it makes this transition here, and we actually look at the area under the curve. So let's go down and show you that thing. So this next cell here is talking about that. So first thing is we'll crank this down to 0. So we'll put 0 signal in, and we'll look at what the power dissipation actually is. I've got this graph down here normalized to 1, which means I go from 0 to 1, but I'm going to get a whole sine wave in one period of a sine wave in here. It makes the integration kind of scaling really easily. So with 0 signal in, we're getting out, we integrate this area under the curve and we get 13.6. So basically I'm taking the plate voltage times the plate current, and I create this graph and I integrate everything underneath here and I get 13.6. Now 13.6 actually is our cue point. I mean, our operating point right here. For if you took 453 times 30 milliamps, you get 13.6. All right, now let's turn up the amplitude a little bit, but let's still stay at class A. All right, so if this is 453, we actually make this hard transition right here at 400 volts. So we could still be around 40 volts and still be class A because we're just going to be swinging back and forth in this region here. Let's turn this up a little bit. Let's turn it up to 10. So what we're doing is we've got an amplitude of 10 and we're running it on here. Now look at this, the power is still about 13.6, and that is because if we're really looking at the integral of this waveform over this this period, and we're really still looking at the area under the curve. And because it's a sine wave, you know, we're adding a little bit here, but we're taking away a little bit on this side. And we kind of stay that way until we get up to 50 volts. We start creeping down just a little bit at 50 volts. What happens when we get over here and we actually start making this switch over? So if we make this a little bit higher, then we'll run all the way up into here. We'll make this switch. So what happens? All right, let's turn it up to 60. So now our amplitude is 60 volts. And look at what's happening here. We kind of got this little bump going on here. And we're turned off down here. Okay. But our plate dissipation is still, now it's up to 12.9. So I've just integrated this area into the curve and I came up with 12.9. All right, we're switching over into class AB. So let's move this up so that we're swinging a much bigger swing. Let's turn it up to 200, so we'll swing down to like kind of down into up to about here. So we're making a big swing. Remember, this is just one tube now, and it's completely on this side, carrying the entire current load, but the other side is actually turned all the way off. So we'll turn this up to 200, and we'll see what happens there as we grow up to 200. And we get even higher up here. All right, we're at 200 volts here. And you can kind of see now this curve's kind of... Now this isn't the voltage curve, so don't confuse that. This is the power curve. And we're actually we're just interested in this from a power dissipation perspective. So we want to integrate this over this period. And we're at 22.5 watts. So we still have it, even though we're way outside of this power dissipation limit, we're running over in this area. By turning off in this area, we're able to sink almost 55 watts into one of the tubes, but we've turned it off over here. So on average, we're still below the power dissipation limit. And if you crank this up even more, you can kind of see it keeps going up. How high does it go? Well, you can sit here and tweak this all day long, but that's kind of tedious. So I created this graph, much like Aiken did on his sheet. That's what this graph down here shows you. So this graph actually moves that slider for you, and it plots. It moves this slider from 0 to about 300, I think. Let me see. There's 0 to 360, and it plots this value out here while this thing is going from 0 to 360. And this is kind of what you end up seeing here. We start out at 13.8. We go down a little bit, then we cross over into AB2, then we start to rise. And we get all the way up, and we get right around here is where the peak power dissipation happens on the plate. And you'll see that we're still down below 25. All right. So this, if you want to really look at things, this table here saves you a lot of effort. If you were to just build everything, which is what Marshall did,
and chose this table almost directly, they're going to be under the 25 watt power dissipation limit for the plate and still get 50 watts out. Actually get a little bit more, about 55. Wow, that's great. Now let's really play around with this thing and do a couple things here. Let's say that some idiot, me, comes in here and puts a 4 ohm speaker on my amplifier. Nothing else changes. Now we just got a 4 ohm. We just got a 4 ohm speaker on here. Now what happens here? This changes to 4. You'll see that the whole slope changes. That's because the reflected impedance looking back into the amplifier, it was 3.4, now it's 1700. So both these curves change. They both switch. Or they both become steeper, and it kicks us way up here. All right. Now if we come down here and we look at this curve down here, we need to rerun this cell. Recalculate this thing. Okay, you can kind of see that if we're down here, we're still in class A, which is below 50 volt swing. We're still looking pretty good. We're still 13.5, And if we zero things out and we don't put any AC waveform in there, we're at 13.6. So we're still at the same spot. But if we crank this up here to 260 now, we kind of see, well, our plate dissipation is now 47 watts. So we'd blow that thing apart. Because look how high this went up. This one side here is now above 100 watts. You can't, even though this one turns off, you're gonna blow those tubes out if you put a 4 ohm load on there. And if we calculate this last thing at that same level, you'll see that we go almost up to 47 watts. So right around here, we'd blow the output tubes if we got about more than 100 volts on our swing on our output transformer. Well, that's not good. Okay, that's the impact of that. Let's look at what happens if we go the other way. Let's say we put a 16 ohm speaker on there. So 16 times 21 squared is going to end up being. The thing calculates up here. My Python's a little slow. The server I'm running off there is a little slow. All right, we're at 7K, and effectively that makes our load lines have a lower slope. Well, we're going to be in Class A a lot longer. We can have a bigger swing and still be in Class A. Then we switch over into Class B. And you kind of see we just kind of violate a little bit because only one tube is on during this time, we're not going to really get beyond our power dissipation limit. So we would be safe if we put in a 16 ohm speaker, but also look at this thing here. This voltage here goes down and we cross the zero grid voltage over here. So we're at 20 volts here and our operating point is 450. If we figure out the power over this swing itself, we get out 26 watts now. We didn't bring this up before, but this number here, when we were back at an 8 ohm load, was about 35 watts. All right, so we can go higher on our impedance and not really have an impact on the performance. But if we go lower, we're going to blow the tubes out. And this is the reason why you want to be very cautious. If your amplifier was designed at 16 ohms and you throw an 8 ohm speaker on there, you might actually blow out the output tubes. All right, let's let this get back up to 8 right here. All right, so our power output was 36. And I got that from looking at 450, which is this number down here, minus 95, which is this number. It's V squared over R, and R is 38, or 3528, which is the reflected impedance. So this is This here is our output swing, so we would be at 36 watts. Well, that's about it. Let's do one more thing here. Let's say that we don't set this at 30. Remember where'd the 30 come from? The 30 came from the EL34 Mullard datasheet. It came from this number right here. Is that a 70% number? I don't know. Does it matter? It doesn't matter. This is where this came from. What if we didn't set it to that? What if you wanted to make it 50% or what? Let's actually calculate what this would be. Oops, let's still got to stay up on that table. We're at 453. Let's do 453 at 30. Let's figure out that power. That's 453 times 0.03. That's 13.6. We already knew that. And 25 watts, that is 50. That's 50%. So we're not even near the 70% number. The 70% number would be 17.5, which at 453 volts is 38. All right, let's crank this up to 38 and see where we go. We're at 37.5 milliamps. We'll let this kind of catch up to us, and we'll see what actually ends up happening. All right, we're at 450 volts still, but we're at 37.5. And you'll see that our Class A operation here actually is over the power dissipation limit of 25 watts. So before we switch over to Class B, we are in violation of our curve. We can go see that if we were to go down, and this voltage here is about 415 volts. So 415 volts times minus 453 minus 415 is a voltage swing of 38. So let's go down to our curve. Let's go down here to our integrating thing where we're actually looking at the plate dissipation. And let's calculate this again here. And we made it, what did we say our voltage was going to be? 38. Let's kick this down to about 40. Now look at that. A 40 volt swing. We get up here to 25, back down to 16. But we're at 16 watts right now. So we're not really in violation of that yet. When we switch over, what happens a little bit? This continues to go up. Are we in danger of blowing our tubes out if we bias it at the 70% number? We won't know that until we run this number down here to run this plot. All right, if we run this plot, we're almost exactly at 25 watt dissipation if our swing gets up to 260 volts. So we're still good at the 70% number. Wouldn't want to go any higher than that. We might risk blowing those out. Now, there's a really good point on the Aiken notes about, if you're playing guitar, do you actually ever sit here at this constant value where your output swing is some value that's kind of constant? And he says that the only time that really happens when you're playing guitar is if you've got a lot of feedback going on. Not feedback in the amplifier, but acoustic to string feedback, so the thing just kind of wails. Because at that point, you're actually driving the amplifier with positive feedback, and you're really kind of hammering it in terms of voltage. So you possibly could sit right around here if your guitarist is actually facing the amplifier and using acoustic feedback to get to drive the thing at a particular note. Okay, well that's where we are. 30 is an okay value, all the way up to 37.5. You wouldn't want to go much higher than that. Anywhere in there, wherever it sounds good would be good. So is a 70% rule valid? Yes, it is for this amplifier at 360 volts. Now, what happens if in our amplifier, because we're not at 360 volts, we are at 450 volts. Remember, our screen voltage is 445. So is any of this valid? Yeah, it's kind of questionable. We don't really know exactly where we sit, because all these curves are going to move up, and what that's going to do is it's going to make this the zero voltage curve actually be sitting around up in here. And what that's going to do is give you more voltage swing. You can get more power output. And because you get more power output, it's possible that you will be in violation down here, because this might cross over the 25. But it could work out that, unless you actually force a sine wave into it at this one voltage, you may never get there. But the Mullard engineers figured out this table, and somehow they did this, and this is optimized to give you 55 watts at 5% distortion for a push-pull amplifier. If you do get near these values, you're good to go. I mean, it's a good design point to actually pick these points, and I believe that's almost exactly what Marshall did when they designed this. I did a little reading, and some people use deoxit for cleaning out their tube sockets, and other people swear not to do that. It does get a little messy. It sprays that crap everywhere. So I'm not using that today. I'm just using some alcohol. I'm going to pour it in this cup here. And I'm going to use this little dental brush. So we pour some in the cup. Get a little on the brush. These come in different sizes, so you can get some that fit right into your pin sockets. Kind of scrub them all out, just like you're supposed to do with your teeth every day. It works pretty well. Same brush worked as on the octal sockets as well. Here's the Mullard tubes that I got from Jerry. These Loner EL34s. GCM was 7900. And he had a match set of 4. And these do look like the mystery tubes that I did have. EL34, right there, made in Russia. Huh. I thought Mullards were made in England. Who knew? So I have his tubes plugged into this because my one tube is kind of failing. I'll just move forward with Jerry's. So I'm using my DC clip-on milliammeters that I got at the estate sale in Los Alamos. Basically these kind of unclip here. It's a transformer here, right here at the end on that head. And the DC going through this transformer actually affects the magnetic field. You just kind of clip it on there. And it measures down to 1 milliamp full scale. This other one here is kind of sticky, so I just kind of clip it together with this zip tie. But there's no unsoldering, no resistor insertion, nothing. I just clip it on. So I clicked on the standby switch. These are rising up, and you'll see that there's an offset. I'm on the 100 milliamp scale. One is actually sitting around 40 milliamps, and the other one's sitting around 33. And this is the second run. The first run I got similar results, but I had the tubes switched in the sockets. So I just verifying the test setup, and I get the same result when I did it 2 different ways. So I definitely have an offset. These tubes aren't matched as well as I thought. Well, sure enough, I should have got all 4 tubes from Jerry, because these 2 EL34s are not well matched. They're off by roughly 10% when I put it in the circuit. You got to see that for when I switched the output tubes themselves.
and the meters actually switch values as well. So I'm going to go back to his place tonight. I'll get the other two tubes. We will match this up and get this thing on the road. That's right, because we got a rock around here at the Valve Studio. Thanks for watching.